magnetic dipole moments. So magnetometer is to compare the magnetic dipole moments or magnetic moments of two bar magnets. The magnetometer is some transparent cuboidal box. And there are leveling screws at the bottom, and there is a compass also associated with it. With the help of compass, we always fix it in the north-south direction. Why north-south direction? Because Earth magnetic field is from south to north direction. In the weekend batch, we will do it tomorrow. Earth ki magnetic field is always from south to north direction. So this box is always kept in south to north direction. There is a magnet, some standard size magnet kept at the center on a pan. So there is a pan which is hanging from some support. There is a cut, and through that cut this string comes out. Okay, so this is a standard magnet inside. Standard means we know what is its dipole moment initially, and there is a pan. In this pan we put that magnet. So south pole and north pole. जब भी हम किसी magnet को release करते हैं, it is free to oscillate. It always align itself in the direction of external field. यह external field कौन सी है? Earth की magnetic field. All the planets have its magnetic field. All the planets which have core have its own magnetic field. Inside the Earth magnetic field, this magnet is always aligned in the direction of the external magnetic field. When we twist it, give it a small twist. From the stable equilibrium position, if we give a small displacement, it will start performing SHM. We kind of derive the formula by comparing it with the electric dipole. Anyone remember what was the formula for time period? Time period of SHM of a magnet when it is slightly given a displacement from mean position. Yes, anyone remember this formula? Magnetic dipole को external magnetic field में रख के थोड़ा सा twist करते हैं, and then we release, it start oscillating about the mean position. Yes, Arnav, Bharat.
I can't recall.
Very nice. What was the formula for electric dipole oscillation? Aradhya, formula for time period of SHM when theta is equal to 0, it is stable equilibrium. We give a displacement to start performing SHM. Time period formula was 2 pi under root I divided by m into b. I is the moment of inertia of this magnet. M is the magnetic dipole moment. B is the magnetic field. In this case, the magnetic field is the horizontal component of Earth's magnetic field, which is BH. In the external magnetic field, when we put a magnet, give a small displacement, it start performing oscillation. The time period of that oscillation is 2 pi under root I by m into BH. M is, this formula is similar to the electric dipole. Electric dipole को हम external field में रखते हैं. This is a topic which is at the end of the at the last of the SL Aurora. It is given separately because it's not included in the CBSE anymore, but there are numericals based on this as in the competitive exam. BH is horizontal component of Earth magnetic field. So there is a magnetic field due to Earth, horizontal component. Right? So magnetic field due to Earth, BH. In that field, when it is free to oscillate, it will be always aligned in the direction of the magnetic field. Theta 0 is stable equilibrium position. थोड़ा सा डिस्प्लेस करेंगे, it start performing SHM. Because it is transparent box, we can count how many number of oscillations are performed in how much time, so we can find the time period. The principle of a magnetometer is we can find the time period, and with the help of time period we get the overall magnetic dipole moment. So if we have two different magnets, एक तरीका तो ये है कि पहले फर्स्ट मैग्नेट रखते हैं, उसका टाइम पीरियड निकालें, उसका मोमेंट ऑफ इनर्शिया कैलकुलेट करें, फिर सेकेंड मैग्नेट रखें और फिर उसका मोमेंट ऑफ इनर्शिया एंड देन टाइम पीरियड. बट द मोमेंट ऑफ इनर्शिया कैलकुलेशन विल बी quite complicated क्योंकि ये 3-dimensional body है. This is a magnet like a cuboidal shape, so therefore we require complex calculation for the moment of inertia. To avoid that हम क्या करते हैं, दो मैग्नेट जिनको कंपेयर करना है. फर्स्ट एप्लीकेशन इज टू कंपेयर ईएमएफ ऑफ to compare magnetic dipole moment of two magnets. We have to compare two magnets dipole moment, which one is stronger and how many times. पहले हम दोनों मैग्नेट के लाइक पोल्स को साथ में लेते हैं, नॉर्थ पोल एंड नॉर्थ पोल एंड साउथ पोल एंड साउथ पोल. दे आर, अब अगर हम दोनों के लाइक पोल्स को साथ में लेते हैं तो ये रिपेल करेंगे, तो इसको हमें जबरदस्ती करके बांधना पड़ेगा. वी टाई देम टुगेदर एंड दिस इज केप्ट इन दैट पैन टू ऑसिलेट इन द अर्थ्स मैग्नेटिक फील्ड. So when both the poles are in the same direction, दोनों का dipole moment will be in same direction. Net dipole moment will become m1 plus m2. हम पहले दोनों के like poles को साथ में रखते हैं, उसका time period calculate करते हैं. Since moment of inertia is like a scalar quantity, अगर पहले का moment of inertia I1 है, दूसरे का I2 है, so it will become I1 plus I2. Dipole moments are m1 and m2. It become m1 plus m2 times BH. इक्वेशन नंबर 1. हमें दो मैग्नेट्स के डाइपोल मोमेंट्स को कंपेयर करना है. द मेथड इज यूजिंग ऑसिलेशन और वाइब्रेशन मैग्नेटोमीटर. मैग्नेटोमीटर इज एन apparatus or device used to compare EMF or compare magnetic field. To compare magnetic moment, we keep two magnets. Like poles are together, overall dipole moment become m1 plus m2. Dhruv, okay. Dhruv,
Yes sir.
you just joined.
Yes sir, मैं 35 मैंने ज्वाइन करके देखा था, तब मीटिंग शुरू नहीं हुई थी, तो मैं थोड़ी देर डिस्कनेक्ट हो गया, फिर अब मैंने करा.
अच्छा, okay. Actually, I was doing this setup for other classes, math class. Actually, we have started offline, so now 5 classes are running offline simultaneously.
ज़्यादा लेट हो गया क्या मैं?
नहीं, कोई बात नहीं, it's okay. We were doing the bar magnet and earth magnetism we were supposed to start, but since in the other batch we are at a different topic. This is another topic, oscillation magnetometer, especially required for the competitive part. Magnetometer is this apparatus. There is a glass box. उसके अंदर एक मैग्नेट रखते हैं and this box is always aligned from south to north direction. अर्थ की मैग्नेटिक फील्ड होती है south to north. So when this is in alignment with the earth's magnetic field, magnet when it is suspended, it will also align in the same direction. Give a small twist from the top, it will start oscillating, and because of being transparent box, we can count and we can find the total time period of oscillation. Time period of SHM of bar magnet formula we did last class, 2 pi under root I by MBH. I is moment of inertia, M is dipole moment, BH is earth's magnetic field, one component, that is horizontal component. So by using this is the principle of magnetometer. हम time period count कर लेंगे, हम moment of inertia या तो measure करेंगे या तो जुगाड़ करेंगे जिससे moment of inertia cancel out हो जाए. To compare the dipole moment of two unknown magnets, M1 by M2 का ratio निकालना है. फर्स्ट केस में हम क्या करते हैं, दोनों मैग्नेट के लाइक पोल्स को, व्हेन लाइक पोल्स आर टुगेदर, लाइक पोल एक दूसरे को रिपेल करते हैं, इसलिए इसको रस्सी से बांधना पड़ता है. व्हेन ये सारे एक्सपेरिमेंट हमने लैब में किए हैं in my 12, अभी ये सब नहीं है आपके सिलेबस में, तो ऐसे भी नहीं है. टू पोल्स दे हैव टू टाई टुगेदर, अदरवाइज दे विल बी रिपेलिंग ईच अदर. उसको इस पेन में रख के एंड देन वी फाइंड द टाइम पीरियड. टाइम पीरियड ऑफ ऑसिलेशन इज 2 पाई अंडर रूट आई अपॉन m1 प्लस m2. सेकेंड सिनेरियो में हम इनको अपोजिट कर देते हैं. देयर पोल्स आर अपोजिट, पहले का साउथ दूसरे के नॉर्थ के साथ. So the dipole moments will be in opposite direction. Being a vector quantity, it will now be subtracted. But moment of inertia can be considered a scalar, or it is a scalar. So that will be only I1 plus I2, and the dipole moment will become M1 minus M2 times BH. This is second question. Understood? Pranay? Magnetometer is an apparatus which is used to compare the magnetic dipole moment of two unknown magnets. Compare करने के लिए पहले दोनों के like poles को साथ में रखते हैं. Find the time period, that came out to be T1. Then their opposite poles are together, then it becomes T2. By measuring this time period, we can find out the dipole moment ratio M1 by M2. Divide the two equation and then take the square. Equation 1 divided by equation 2, या स्क्वायर करके डिवाइड करो या पहले डिवाइड करके स्क्वायर करो, एक ही बात है. बेटा कुछ समझ में आ रहा है?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, very nice. This is in the SL. If anyone wants to see, ये बिल्कुल ही irrelevant नहीं है. This is in SL Aurora, and this part is asked in the exam because this formula we have even in the NCRT. So when there is a magnet in the external magnetic field, which is used in Earth's magnetic field here, it start oscillating like a SHM. Divide the two equation and then do the square, or maybe let's square first and then do the divide. So if we have to compare the dipole moments, M1 by M2 ratio we have to find. Equation 1 square divided by equation 2 square. When you prepare for the school exam or UT exam, इसमें बहुत सारा part है जो आपको कट करना है. So I think you guys are smart enough. School के लिए जो syllabus थोड़ा सा reduce हुआ है for the board and exam, that you don't have to prepare while preparing for this school. Or T1 square by T2 square. So this 2 pi become 4 pi square. Root will be gone. बाकी सब कैंसिल आउट हो जाएगा. इट विल बी m1 प्लस m2 और दूसरी इक्वेशन में m1 माइनस m2. स्क्वायर करके डिवाइड कर दो. t1 स्क्वायर बाई t2 स्क्वायर इज m1 माइनस m2 डिवाइड बाई m1 प्लस m2. क्रॉस मल्टीप्लाई और कंपोनेंट और डिविडेंडो व्हाटएवर यू वांट टू अप्लाई, वी कैन फाइंड द m1 बाई m2. मैंने थोड़ा शॉर्टकट कर दिया. स्क्वायर करेंगे 4 पाई स्क्वायर, इसका 4 पाई स्क्वायर दोनों कैंसिल. I1 plus I2, I1 plus I2 cancel, BH cancel. Only these two terms will be left, M1 plus M2 and M1 minus M2. When we divide these two equations, square and divide, cross multiply करके, I think M1 by M2 will come out T2 square plus T1 square divided by T2 square minus T1 square. This is the ratio of magnetic dipole moment. M1 by M2 will be T2 square plus T1 square by T2 square minus T1 square.
I have a question. In the diagram, it's shown that the like poles are together.
है ना. और g की वैल्यू क्या हो जाएगी? अंडर रूट ऑफ a, राइट. अब मामला क्या है?
Yes, Arnav. Can you ask the question again in the diagram?
So where you've shown that the like poles are together, वो चिपकाए हुए हैं क्या साथ में?
Like poles are together, then
So
moment.
are the magnets stuck together?
No, they are not stuck together. We have to tie them with a string.
You have to tie
And
them.
we
I
have
was
to-
wondering कि कैसे they're together because the like poles won't
Yes, yes,
repel.
yes, yes, yes. They are repelling each other. We have to keep them tied together with a string. Otherwise, north will repel. Okay, there is one more application of magnetometer, which is to compare the magnetic field produced by two unknown magnets. This is the comparison of two dipole moments. Dipole moments or magnetic dipole moments is compared with the help of T1 and T2. So दोनों के like poles को साथ में रख के बांध देते हैं. We find its time period T1. Then unlike poles are together and then we find its time period again. And by using those T1 and T2, we can find the ratio of magnetic dipole moment of two unknown bar magnets. Next is to compare magnetic field produced by two unknown magnets. This is clear? I'm getting the same result after cross multiplying.
Yes, sir.
So symbol T1 is magnetic time period when the like poles are tied together. T2 is the time period when opposite poles are tied together. Second application is to compare the magnetic field produced by two unknown bar magnets. We don't know their dipole moment, so we cannot apply that formula. These are two unknown magnets. So in a way, it will also depend upon their dipole moment strength only. The one which has a greater dipole moment will produce stronger magnetic field. Second application is to compare magnetic field produced by two bar magnets. Okay, again, using the magnetometer only, we have to compare this. Magnetometer के अंदर एक standard magnet रखा हुआ है already. Inside the magnetometer, some standard magnet is kept, which is oscillating in the Earth's magnetic field. Or there's a pan. That pan is actually attached to the string in the actual setup. अभी जो बहुत सारे एक्सपेरिमेंट यहाँ से हटा दिए गए 12 से, that we do in the college. In the engineering also there is experimental physics and experimental chemistry course.
सर जेई में तो एक्सपेरिमेंटल फिजिक्स आती है.
वो तो अलग चीज है यार, वो तो केवल एरर कैलकुलेट करने के लिए आती है. एक्सपेरिमेंटल फिजिक्स नाम का जो चैप्टर है, एक्सपेरिमेंट में एरर कितनी हुई. आई एम टॉकिंग अबाउट द एक्चुअली परफॉर्मिंग दिस मैग्नेटोमीटर, मैग्नेट, अपने घर की छत पे जाके घर की मैग्नेटिक फील्ड निकालना, ये सब प्रोजेक्ट में है अभी, नॉट इन द प्रैक्टिकल, बट यस इट इज आस्क्ड कैलकुलेट द मैग्नेटिक फील्ड एट योर place, which is a fun, but unfortunately that part is not in the syllabus and not required for this course. Some noise is coming. Kindly mute yourself. इसका भी है. Rudransh, yes, thank you. Bharat, you are saying something?
Nothing, sir. I
Yes,
just
you are
muted.
chat. My device had very low battery, so why I came late. Okay, no problem. There are some challenges in obviously online classes. Battery, internet, so and so and so issues. Right, Arnav?
Yes, sir.
Fine. You're getting this concept?
Yes, sir.
Okay.
I just
Magnetic
wish we could
field.
try this out in real life and actually see it for ourselves.
Okay, did you find it
No, I wish we could try it.
in the Google or actual?
Actually.
You want to do this?
Yes, sir.
Yeah. But as I'm saying that unfortunately this part has no weightage in the marks. So in college, like in IIT Kanpur, there are two courses on this: experimental physics and experimental chemistry. Most of the theory that you are learning here, you will be doing practical as a practical course, as a 5 credit course. No theory, only practical class, only practical course. So South Pole, North Pole, there is a magnet. Okay, that's the basic difference between other some or the other foreign university course. Like in IIT, whether you do theory or not doesn't matter, but practical you are not supposed to skip in any branch. If you attend a practical, you will get 1% marks. If you miss a practical, minus 10% marks will be deducted. So you learn only when you do practical. Anyways, this is the time period where there is no other magnet. हमने बाहर कोई मैग्नेट नहीं रखा, केवल अंदर जो मैग्नेट था उसी का ऑसिलेशन करके उसका टाइम पीरियड कैलकुलेट करके. When no magnet is kept outside, only inside magnet is oscillating in Earth's magnetic field itself. Second scenario, हमारे पास दो मैग्नेट्स हैं और दोनों के मैग्नेटिक डायपोल मोमेंट को दोनों की मैग्नेटिक फील्ड को कंपेयर करना है. So in the same line at certain distance, बाहर एक स्टैंड पे we keep that magnet. So when first magnet is kept at a certain distance, it will produce its own magnetic field also. This is the magnet number 1. Now the magnet is oscillating in overall magnetic field of BH plus B1. BH is because of Earth, B1 is because of this magnetic field. When first magnet is kept outside at certain distance, the magnetic field of that magnet plus Earth magnetic field, both will be in same direction, it will be added. First magnet is kept outside at a certain distance. The time period of oscillation is again measured, and this comes out to be, since the oscillating magnet, if magnet is still the same, so its moment of inertia will be same, its magnetic dipole moment will be same, but the magnetic field has changed from BH to BH plus V1. Right? When there is magnet number 1 or M1 is placed. At this same distance, again we replace that magnet by the second magnet and we find the dipole, we find the time period in the presence of that second magnet. Are you able to see this or is it a small?
Sir, it is visible.
It's visible, na? Okay. Hope so. Now the first magnet is removed and the second magnet is kept. Once you asked some question about the test. Current electricity test has not happened yet.
Yes, sir.
So this week it is magnetic moment, magnetic field, because we have been discussing those recently. So I asked chapter number 3 will come later. This is the standard magnet. और बाहर हमने रख दिया magnet number 2. This second magnetic field we have to compare. This second magnet which is kept outside the same line will produce its own magnetic field B2. So the magnet is oscillating in this new magnetic field of BH plus B2. So when second magnet is kept outside, पहले हमने बाहर कुछ नहीं रखा, उसका टाइम पीरियड कैलकुलेट करेंगे, फिर बाहर फर्स्ट मैग्नेट को रख के in the same line we'll find out the time period, that's T1, and then second magnet is kept outside and again find the time period, that's 2 pi under root I upon m into BH plus B2. These are the three situations. पहले no magnet, then first magnet and then second magnet. Right? Time period T is without any magnet. अब हमें calculate करना है ratio of B1 and B2. तो थोड़ा हम standard solution कर लेते हैं. Equation number 1. वैसे तो square करना चाहिए, but चलो अभी हम direct कर लेते हैं. Equation number 1 divided by 3, that is first one. And another will be equation number 1 में एक बार 2 को डिवाइड करेंगे और 1 में एक बार 3 को डिवाइड करेंगे. These are the two simultaneous calculations. So because these calculations are similar only. पहले मैग्नेट ने V1, दूसरे मैग्नेट ने V2. So overall field is BH plus B1, BH plus B2. When no magnet was kept outside, it is only BH. 1 divided by 2, that will become T by T1. 2 pi gone, I gone, m gone. This will become root of नीचे BH ऊपर BH plus B1. Please check and verify the question is correct or not. Without any external magnet, with the first magnet, time period is T1. Without any magnet, time period is T2. With the second magnet, time period is T2. Again, T by T2, 2 pi gone, I gone, m gone. This will become BH plus B2 and divided by BH. Is it correct? Is it correct? Please check. बाहर वाले मैग्नेट को पहले फर्स्ट मैग्नेट फिर सेकंड मैग्नेट एंड देन वी फाइंड द टाइम पीरियड डिवाइड एंड देन डू द स्क्वायर ऑन बोथ द साइड. T स्क्वायर बाय T1 स्क्वायर, इधर स्क्वायर से रूट हट जाएगा. BH by BH is 1 plus P1 by BH. Same step on the other side. T square by T2 square is 1 plus B2 by BH. 1 को लेफ्ट साइड में ले और फिर क्रॉस मल्टीप्लाई. B1 by BH is equal to T square by T1 square minus 1. Similarly, B2 by BH is T square by T2 square minus 1. Cross multiply to get B1 and B2. B1 is T square by T1 square minus 1 times BH. B2 is T square divided by T2 square minus 1 into BH. Divide B1 by B2. Question number 4 and 5. So if you divide the two, B1 by V2, P1 by V2, that will become T square by T1 square minus 1 divided by T square by T2 square minus 1. That's the ratio of the magnetic field. हम तीन अलग अलग टाइम पीरियड कैलकुलेट करेंगे विदाउट एनी एक्सटर्नल मैग्नेट, with the first magnet T1, with the second magnet T2, and the ratio of magnetic field produced by the two magnets will be given by this. There are few numericals on this also in the SL. I'm just taking the example of SL because that is the book we have been following. So I'm taking those extra concepts जो book के last में है, which is used to be in the syllabus earlier. अभी थोड़ा सा syllabus में theoretically नहीं है, but yes, numerical may come, numerical used to come in the competitive exam. Any part not clear? वैसे तो simple सी maths है, बस divide करना है. Physics का concept सिर्फ इतना है, अंदर एक magnet रखा हुआ है और हम बाहर से magnetic field को change कर रहे हैं. BH is because of Earth, B1 is because of that magnet. As a result, the total magnetic field become BH plus B1 in the first case, BH plus B2 in the second case. Done? Yes, but understood? Yes, sir. Okay, so another new concept called as tangent law. भी हम थोड़े concept कर लेते हैं because जो doubts होंगे वो last के 15-20 minutes में you can WhatsApp or send in the group. We will discuss those doubts also. Tangent law or tan law, which is a very obvious thing जो हमने vector में पढ़ रखा है. Tangent law is बहुत सी obvious चीज हमने पढ़ी थी vector में. If there are two perpendicular vectors A and B और उनका resultant vector है vector R. So हम ऐसा बोलते थे कुछ A and B are the components of vector R, rectangular components. If this angle is theta, then tan theta is B by A. But this is the tangent law, which is a very obvious thing in vector. So tangent law says if there are two perpendicular magnetic field, if there are two perpendicular magnetic field, अगर ये दो perpendicular magnetic field है किसी जगह पे और हमने एक compass या magnetic needle को रख दिया, in which direction that needle will point? In the direction of B1 or in the direction of B2 or in the direction of the resultant? If suppose there is a needle free to rotate, in which direction it will align? B1, B2 or along the direction of the resultant? Which direction the needle will point? Magnetic needle or compass or dipole always align towards the direction of net magnetic field. B1, B2 का जो resultant है B उसकी डायरेक्शन में that compass will align itself. Why? Because theta 0 only is the stable equilibrium position. Now the tangent law says if there are two perpendicular magnetic field present, the tangent of angle of deflection of the compass is equal to the ratio of those two fields, which is nothing but the same as a normal vector formula. दो perpendicular vectors का अगर resultant है vector r, then resultant will be inclined at an angle theta such that tan theta is v by a. So likewise here tan theta is v1 by v2. दो perpendicular vectors है अगर किसी region में there any compass is placed, that compass will always align itself in the direction of external net magnetic field, and if it is inclined at an angle theta, tan theta is equal to ratio of the two field. Tan theta is v1 by v2. What is so special then? हम पढ़ क्यों रहे हैं इसको अलग से जब ये इतनी obvious चीज है? Because actually this is used in designing some another type of galvanometer. इसमें बस most of the time what we do that one of the magnetic field we use earth magnetic field BH. So B upon BH is equal to tan theta. B is produced by some magnet and B2 is because of earth. One of these two magnetic field is taken as earth's magnetic field BH, horizontal component. So B upon BH become tan theta. Yes. Statement में लिख नहीं रहा हूँ क्योंकि थ्योरी में ये टॉपिक आएगा नहीं. Statement is also obvious. अगर दो perpendicular vector है और उनका resultant angle theta बनाता है, then tan theta is b2 by b1. Tan theta is ratio of the two magnetic field. The application of this law is in the tangent galvanometer. हम tangent galvanometer क्या होता है वो तो बाद में समझेंगे, पहले ये समझते हैं why do we need another galvanometer जब हम एक already बना चुके हैं. We have already moving coil galvanometer. We saw the working. Moving coil galvanometer में अंदर एक coil होती है, coil में current pass करते हैं, it experiences a torque, and because of the torque it rotates, and the rotation of the coil gives the twisting of spring. Spring के साथ pointer attach होता है, and it also shows deflection on the screen. That is for moving coil galvanometer. What is the need or what is the use of another galvanometer when we have one already? This question का आंसर हमें मिलेगा in this particular working principle. So tangent galvanometer में होता क्या है? Tangent galvanometer has one vertical circular loop of n number of turns. ये एक बड़े से vertical plane में there are n number of turns in the loop, and these are connected to the 2 point or 2 terminals of the loop. Vertical plane में एक circle loop होता है और उसके center पे एक horizontal plane में compass रखा होता है. In the horizontal plane there is a compass placed. Always this vertical plane is again chosen to be magnetic meridian so that इसके along earth की magnetic field already होगी. In this plane the earth magnetic field is already existing. यहाँ पे कुछ support होता है उसके ऊपर रखा है जैसे हवा में float नहीं कर रहा है. To measure a current, जिस भी current को measure या detect करना है, it is passed in this loop. n number of turns है इसमें and the radius of loop is r. Number of turns in the loop is n. Number of turns in the loop is n. Radius of the loop is r. Radius of loop is r. Correct. Now इसमें जैसे हम करंट पास करेंगे देयर विल बी अ मैग्नेटिक फील्ड प्रोड्यूस्ड बाय दिस सर्कुलर लूप में क्लॉकवाइज करंट है तो हम अंदर की तरफ आएगा सो देयर इज वन मोर मैग्नेटिक फील्ड इज प्रोड्यूस्ड व्हिच इज गोइंग इनटू द प्लेन सो इसका मतलब वो बी के परपेंडिकुलर है बीएच के बी This compass, which is kept at the center, has two magnetic field produced. One is because of Earth, another is because of this current. So, अगर हम इसका top view देखेंगे, in this compass, there is B and there is BH. ये दो magnetic field आ गई. One because of Earth, another because of the current produced by this current pass into this loop. और यहाँ पे एक कंपस होता है बीच में दैट कंपस विल ऑलवेज बी अलाइंड इन द डायरेक्शन ऑफ द रिजल्टेंट जिसका एंगल हम मेजर करते हैं द एंगल इज मेजर्ड फ्रॉम द स्केल
सर ये माइक्रोमीटर है।
नहीं ये माइक्रोमीटर नहीं है टेंजेंट गैल्वेनोमीटर
So this we call it tangent micrometer.
नो इट्स टेंजेंट गैल्वेनोमीटर द सोक्रेटिस डांस
यस सर।
सोक्रेटिस और गूगल
सर इतना तो आता ही है।
हाँ ऐसे कुछ स्केल पॉइंटर होते हैं 0 30 60 सो वी मेजर दिस एंगल और इस एंगल के हेल्प से वी कैन डिटेक्ट दिस करंट हाउ नंबर ऑफ टर्न्स n है रेडियस इज r करंट इन द लूप इज I सो मैग्नेटिक फील्ड एट द सेंटर ऑफ सर्कुलर लूप फॉर्मूला था mu naught ni by 2r mu naught I by 2r था because there are n number of turns if this pointer is at an angle theta तो tangent galvanometer का principle होता है tangent law and by tangent law we can see that B is equal to BH tan theta. B is equal to BH tan theta. B आ गया mu naught n I by 2r is equal to BH times tan theta. क्रॉस मल्टीप्लाई कर लो I is 2RBH divided by mu naught into n times of tan theta. I is that current, theta is the deflection shown by the pointer. I is 2RBH by mu naught n into tan theta. R radius है जो किसी गैल्वेनोमीटर के लिए कांस्टेंट है किसी एक फिक्स गैल्वेनोमीटर में टाइम के साथ रेडियस तो चेंज नहीं होगी. This is the radius R. Number of turns constant है mu naught is permeability constant BH is anyways constant so सारी की सारी term everything here is constant इसको हम एक constant K से denote करते हैं I is equal to K tan theta this is the formula for tangent galvanometer where K is 2RBH upon mu naught n is called रिडक्शन फैक्टर रिडक्शन इसलिए क्योंकि एक बड़ा सा फॉर्मूला छोटे में रिड्यूस हो गया और कोई इसका लॉजिक नहीं है रिडक्शन फैक्टर with the help of the angle shown by the compass at the center we can get the idea of current and this current is very sensitively measured even if it is very small. That is the difference between this galvanometer and moving coil galvanometer and that is why we are preferring this or using this even when we have one already magnetic moving coil galvanometer. Last वाले sentence को सरल भाषा में समझाते हैं.
What was
अगर
L?
हमें हाँ बेटा,
L क्या था यहाँ पे?
there is L. I is the current.
Oh, that's I. Okay.
That's not L, that is I. I is the current in the loop. अब जो मैंने लास्ट सेगमेंट बोला उसको फिर से समझते हैं। जो नॉर्मल गैल्वेनोमीटर था उसका प्रिंसिपल क्या था? मूविंग का गैल्वेनोमीटर, करंट पास करते हैं, करंट के हिसाब से टॉर्क लगता है, एंड दैट टॉर्क विल रोटेट द कॉइल। सो कॉइल का कुछ मास होगा, कुछ मोमेंट ऑफ इनर्शिया होगा। सो सर्टेन मिनिमम amount of torque is required to get a visible deflection. Means if current is very small, then that method is not very suitable. स्मॉल करंट को, स्मॉल मतलब माइक्रो एम्पियर के करंट को मेजर करने के लिए वी प्रेफर टेंजेंट गैल्वेनोमीटर, और इसलिए इसको हम माइक्रोमीटर भी बोल सकते हैं, मिलीमीटर भी बोल सकते हैं, बट दिस इज मोर सुटेबल और दिस इज यूज्ड ओनली फॉर अ वेरी स्मॉलर करंट which cannot be sensitively measured by moving coil galvanometer. छोटी करंट के लिए टेंजेंट गैल्वेनोमीटर प्रेफर करते हैं. When current is large, then we use moving coil galvanometer, and this we will prove also. Tangent galvanometer is used for smaller currents. When current is very small, the sensitivity is very high. Current sensitivity क्या था? Definition of current sensitivity in the galvanometer. Anyone? Current sensitivity, what it is defined, and formula तो छोड़ दो, formula यहाँ applicable नहीं है, but what is the current sensitivity of a galvanometer? Deflection per unit current. Deflection per unit current was defined as current sensitivity when it is used to measure the current. Deflection per unit voltage is defined as voltage sensitivity. तो हम ये statement यहाँ पर use कर रहे हैं that for smaller current, tangent galvanometer is more sensitive than the moving coil galvanometer. छोटे करंट को एक्यूरेटली डिटरमाइन करने के लिए we have tangent galvanometer. Moving coil galvanometer भी deflection शो करेगा, but वो इतना small सा होगा that we will not be able to visibly detect in the pointer of moving coil galvanometer. Current sensitivity होता था deflection per unit current. यहाँ पर की बहुत छोटी करंट है, इसलिए d theta by di that we will use. Okay, d theta by di, और हमें I पता है थीटा के टर्म्स में, so we can also represent this as 1 upon di by d theta. I is k times tan theta. इसको डिफरेंशिएट कर लोगे थीटा के रेस्पेक्ट में, तो tan थीटा का डिफरेंशिएशन होता है sec square theta. So 1 upon k sec square theta. Sec square theta can be written as 1 plus tan square theta. It can be written as 1 plus tan square theta, and tan theta can be written as I by k. Current sensitivity is deflection per unit current d theta by di. इसको हमने थोड़ा सा रिवर्स कर लिया, 1 divided by k into 1 plus tan theta is I by k. स्क्वायर लेके एलसीएम लेके ऊपर कर लो, k divided by k square plus I square. This is the current sensitivity. In this formula, I square is in the denominator. The smaller current, more will be sensitivity of this tangent galvanometer. स्मॉलर करंट के लिए सेंसिटिविटी ज्यादा है, so we should prefer tangent galvanometer while measuring the smaller current. It will measure a smaller current accurately as compared to the moving coil galvanometer. Right?
Yes, sir.
Okay, one more thing we have to prove here. Objective में question आता है, for what deflection this is showing maximum sensitivity or this is showing least error. For example, meter bridge के केस में क्या था? Meter bridge most sensitive कहाँ पर होता है? When deflection is at the midpoint. 40 से 60 के बीच में near the 50 centimeter mark, if there is a deflection point, it shows most sensitive, maximum sensitivity, or it shows least error.
Into 4, 23 into 4, 92. Sum of 3 days, the last may be 4 is Thursday, Friday. 28 into
Now we have to prove that error in current is minimum at certain angle. कौन सा angle है वो? बेटा ये कुछ समझ आ रहा है? Mr. Bharat?
Yes, sir. समझ आ रहा है. That is why I'm taking in class notes.
Okay, that is why you are taking in class note because of that. Good. Good answer. Error in current. Meher? Meher? Error in current is error divided by actual value, di by I. Di is the error in current, I is the actual value of current. So di हो जाएगा k sec square theta d theta cross multiply करके, and I is k tan theta. So that will be yeah. Phase sec square theta is 1 by cos square theta, tan theta is sin theta by cos theta, cos gone, d theta divided by sin theta into cos theta, 2 से ऊपर नीचे मल्टीप्लाई कर लोगे तो ये बन गया 2d theta divided by sin 2 theta. The fractional error in the current is 2d theta by sin 2 theta. For minimum error, sin 2 theta maximum होना चाहिए, and the maximum value is 1 when theta is 90 degree. Sorry, 2 theta is 90 degree. So minimum error के लिए theta होना चाहिए 45. So when this deflection is exactly at the middle, 45 degree, the error in the current measurement is minimum. It's most sensitive when theta is 45. Right? Tangent galvanometer की जरूरत क्यों है? Smaller currents को sensitively या accurately measure करने के लिए we require tangent galvanometer. Working principle is tangent law. With increase, we will always try to align the magnetic moment or magnetic compass at 45 degree When theta is 45 degree, it shows minimum error. तो ये जो कुछ एक्स्ट्रा टॉपिक थे वो हमने कर लिए. Now we have to start the doubts. So any doubt that you have? Yes.
तो सर एरर तब भी रहेगा?
एरर तो हमेशा रहेगा यार. एरर तो कभी भी नहीं जाती है. एरर को हम कम कर सकते हैं, एरर खत्म नहीं कर सकते. एरर विल ऑलवेज बी देयर, बट हम हमेशा ऐसा करने की कोशिश करते हैं कि वो कंपास 45 डिग्री पे शो करे. सो वेयर इट इज 45 डिग्री देन एरर इज मिनिमम. जैसे हम मीटर ब्रिज के केस में हमेशा कोशिश करते हैं दैट बैलेंसिंग लेंथ शुड बी एट द मिडल 50 सेंटीमीटर के आसपास. क्लियर?
Yes, sir.
Right now, any doubt that you have from the portion that we did in class last week or any other topic? कोई doubt हो, please. The last 10-15 minutes left. Any
Sir,
question,
test of-
any topic, any concept? Yes, beta.
सर टेस्ट ऑफलाइन भी दे सकते हैं?
Test offline भी दे सकते हैं. What time is test? 9 AM. First
Sir,
slot का नहीं दे
शा-
सकते.
सेकंड
हाँ,
स्लॉट
वाला
का ले
दे
सकते हैं ना?
second slot का दे सकते हैं.
ओके सर.
Okay, if there is no doubt, then beta bye bye. The doubts होने चाहिए. अभी time है. We have around 15 minutes. Any doubt, any topic, any question?
So could you maybe revisit the concept of internal resistance of a cell and terminal potential and all of that?
Concept.
Yes, sir.
You
I was
can
actually
go through
revising
the
and I was
video.
getting confused when I was reading it again.
Okay. Wait, my phone battery is going. It's 2%. Let me bring the charger. Yes. Yes, Arnav. Now you are saying something. The
So I was
internal resistance of a cell is resistance offered by the
the internal resistance, terminal voltage, terminal current, and when cells are connected in charging and in opposite polarity.
internal resistance. क्या होता है सेल के अंदर electrolytic solution that offers some difficulty in moving the current. That's called
थर्ड चैप्टर
internal
में था ना ये?
resistance. हाँ बेटा थर्ड चैप्टर में था. क्या बात है. वेरी गुड. क्या था ये भी याद है? नहीं.
सर याद है.
क्या होता है इंटरनल रेजिस्टेंस?
सर बैटरी के बाद था. ईएमएफ था एक तो, इलेक्ट्रोमोटिव फोर्स.
Electromotive force is the work done by battery in moving a unit charge.
Yes,
और
sir.
उस चार्ज को मूव करने में जितनी डिफिकल्टी प्रोड्यूस होती है बिकॉज ऑफ इलेक्ट्रोलिटिक सॉल्यूशन, दैट्स कॉल्ड इंटरनल रेजिस्टेंस. internal resistance of a cell is always in series with the battery. So I don't know which part is exactly doubt, so I can go directly to that. Terminal potential difference.
Yes, sir. Terminal potential and all of that.
When there is nothing connected outside, this is open terminal. These two electrodes, one gets oxidized, so there is a loss of electron, it becomes positively charged. Another has excess of electron, it becomes negatively charged. Because of this terminal potential, there is a one side charge accumulation. The one become higher potential, other become low potential. Potential difference is called EMF. If there is no current at this time, there is a resistance. That resistance is connected in series with the battery terminal, but no current is passed. No current means no potential difference will be lost here. So terminal potential across this cell will be equal to EMF when there is no current. Right now, when we connect this to external circuit, some battery or some bulb, current will be passing from one battery terminal to another terminal, and in between there is a resistance. That internal resistance will cause potential drop. So right, so internal resistance will be losing, some work is done against that internal resistance, and that will cause the potential to drop. So battery is discharging. Battery is discharging means battery is providing current. So from terminal A to terminal B, from positive terminal to negative terminal, when you go, battery को इस internal resistance के against work करना है, and that is why its EMF is lost.
So that is known as battery mechanism.
बैटरी मैकेनिज्म, बैटरी काम कैसे करती है, राइट? ये जब करंट बाहर निकल रही हो मींस व्हेन सेल इज डिस्चार्जिंग. जब सेल डिस्चार्ज हो रहा है मतलब सेल करंट प्रोवाइड कर रहा है, सेल से बाहर की तरफ करंट आएगी, P इज इक्वल टू E माइनस IR. थर्ड सिचुएशन इज जब सपोज हमने इसमें बाहर से एक दूसरा सेल लगा लिया जिसका EMF इससे भी ज्यादा है, which is more powerful, so it is sending current into the battery. If there is a current coming into the battery, means work is done on this internal resistance or on this cell by the external source, by the external current, जो कि reversible reaction होती है in the storage cell. इन्वर्टर के अंदर जो बैटरी होती है, लेड स्टोरेज वेल. अब हम जा रहे हैं करंट की डायरेक्शन में, so the potential difference will become E plus IR. Potential across the terminal is greater than EMF जब सेल चार्ज होता है, less than EMF जब सेल डिस्चार्ज होता है, equal to EMF जब कुछ नहीं होता. There is no connection with any part of the circuit. Right?
Yes, sir.
Okay, I think that's it.
Yes, sir. Thank you.
So bring your numerical doubts also for the Friday class. Solve numerical, do the practice. This Sunday, chapter number 4 test is there, I think. Okay, thank you.